Welcome back at part 2 of this episode on singular Sturm-Liouville problems. As promised, part 2 is a case study, an example. And for the example I chose Legendre's equation and Legendre Polynomials, as we shall see, concentrating on the subject of this episode, which is the singular Sturm-Liouville problem. So our aim was to extend the scope of Sturm-Liouville theory so as to include differential operators that have regular singular points. And Legendre's equation, as we shall see, is a good example of that. And so in the first part of this episode, we revisited the proof for self-adjointness, so the conditions for self-adjointness of the differential operator and the problem as a whole. And we saw that we can often expect that we shall be able to relax the conditions for self-adjointness, because the very fact that the equation has regular singular points means that the function that is often called p, which is the prefactor of the highest order derivatives, has a zero, and that same function p plays a key role in the condition for self-adjointness, and the fact that it has a zero helps to make sure that we have self-adjointness. So we see that very nicely, the regular singular points and the Frobenius theory that we use to analyze what happens to the solutions at the regular singular points very nicely falls into place if you put it in the context of Sturm-Liouville theory. And the harvest will be orthogonal functions. Then, of course, if you have self-adjointness, you can expect to have orthogonal functions. So we will see. We'll study this now in the context of Legendre's equation and Legendre functions. So Legendre's equation is over here, as we met it at least in the exercises of chapter 5. We're working on chapter 5 was about Frobenius theory, and that is a theory and a method that has been developed and is suitable to study these kind of equations. And the key point is that Legendre's equation is not in standard form and cannot be written in standard form for second order linear differential equations as in chapter 3, because it has a prefactor over here, 1 minus x squared, and that has zeros for x is 1 and x is minus 1. Now, then applying Frobenius theory, you can put the diagnosis that is regular, those are regular singular points, and you can use the Frobenius theory to figure out what kind of solutions this equation has, whether or not they are singular at singular points, etc. So we'll come to that. But the first step that is of relevance to us now, as regards to Liouville theory, is that this equation can be written in Sturm-Liouville form, at least the differential operator. So if you look at this part of the differential operator, you see this minus 2x is the derivative with respect to x of this prefactor of the y double prime. That is what is written here, so I say the dx acting on this combination produces that. Now we put a minus here, that is a convention in Sturm-Liouville theory. As a result, the eigenvalues will be positive, increasing instead of decreasing. So for that I have to multiply the whole equation by minus 1, and if I then put this term to the other side, it gets plus again, and if I write lambda for nu times nu plus 1, you get the standard eigenvalue equation for y. So this differential operator L, if if you write an eigenvalue problem for that, standard notation with lambda for the eigenvalues, that is exactly equivalent to the Legendre equation. So we see Legendre's equation as such has the form of a differential equation that fits Sturm-Liouville theory, but it is not standard because in regular Sturm-Liouville theory this function is not allowed to have zeros. No. In part 1 we have seen that there's possibilities to import such equations into Sturm-Liouville framework. And in that framework then we will have these, identify these definitions. So P of x is that coefficient, Q of x in this in the sense of the Sturm-Liouville formalism 0 here, and the weight function is very simple. That is the weight function at the right hand side. So if you read it as an eigenvalue problem, and it is just 1 here. So this is a simple form. Then based on the theory, all the lectures on Sturm-Liouville theory and part 1 of this lecture, where we studied in detail how to, if it is possible, and if so, how, to satisfy conditions for self-adjointness, we see at the regular singular point, P, let's say that x is 1 or x is minus 1, then the P is 0. And hence, if you supplement the problem with the conditions that the solutions, or indeed any function that you would like to allow in the context of your work, and the derivative are bounded, so that the Wronskian matrices of the functions are bounded at the regular singular points, then the problem will be self-adjoint. And the conclusion of this, if you would solve Legendre's equation, it has solutions that are all, as we will see in the next slide, it has solutions that are singular, but it also has polynomial solutions. Those are called the Legendre polynomials. Those remain finite. So there's only, and the conclusion is only the Legendre polynomials satisfy both, and I do, the Legendre's equation, the Legendre polynomials do satisfy this equation, Sturm-Liouville formulation of Legendre's equation, and these boundary conditions. If you require that the functions remain finite, then only the Legendre polynomials are allowed. And hence, if you do satisfy those boundary conditions, then the problem will be self-adjoint, and hence it follows that the set of Legendre polynomials itself is an orthogonal set and a basis. And the proof of that is exactly the same as that we had in the context of regular singular Sturm-Liouville problems. If you have this self-adjointness, then it follows that any eigenfunctions that belong to different eigenvalues are automatically orthogonal. Now, and in this case, the Legendre polynomials have as eigenvalues n times n plus 1, and they exist only if n is a natural number, so 0, 1, 2, 3. And then all those eigenvalues are distinct, different from one another. And from that it follows with the theorem that we had for regular singular Sturm-Liouville problems, if you have self-adjointness and the eigenvalues are different, then automatically the eigenfunctions are orthogonal. So it follows from this that the Legendre polynomials are orthogonal with respect to this inner product which plays two roles in the theory. First of all, this is to use this to define self-adjointness, that was here. So you have to be able to move the differential operator from one slot to the other. That was the check of the condition on self-adjointness. And it is used to define the orthogonality of the functions, and then in principle this weight function r of x occurs here. But that is one here. So the Legendre polynomials are orthogonal with respect to this inner product. And that statement is here. The inner product of Pn times Pm is 0 as long as n is different from m. Now let's have a look at that. So this slide is about Legendre polynomials, orthogonality. Actually, I have sliders here, so I can change these functions, and you see all the Legendre polynomials. They occur in the right, and the expressions occur. You would find them if you solve, for example, Legendre's equation for integer numbers of the parameters. And there are other ways to find them, by the way. These are very famous functions. And this is how they look. Now, so they are orthogonal, so in the top plot, I just can pick two values of n and m, and then I get here the graphs of those functions, and their expressions occur at the right. So you see, for example, if I have an even value of n, 4 or 6, then you get polynomials that have only the even powers of x, so there are even functions. That is also clear in the graph. This is say the blue one is the P6. It has 6 intersections with horizontal axis, and it is symmetric in the vertical y-axis. So it's an even function. This one is odd, if n is 3. And below here is the graph of the product. Now, if one function is even and the other one is odd, the product is odd, and hence it's not difficult to see that the integral of this function is 0, because any excursion of the function that occurs left from vertical axis also occurs right, but then mirrored. So with a change in sign, and if you integrate them up, you get 0. But that is not so obvious if both are odd, for example. So if I change this, I get the odd function, and then the product is even. So then it's actually surprising. It's apparently, if you integrate this function, that is the definition of those functions being orthogonal. If you integrate them from the one regular singular point to the other one, from -1 to 1, the integral is 0 of the product. So apparently the sum of all these little areas is guaranteed to be 0, whatever the values of n and m are, except of course if they are equal, like this. If both are... and of course you get what is called a norm, you get the product of the function itself, and we calculate the norm of it. So, inner product of the function with itself. So those are the Legendre polynomials. They all have expressions. Now, you don't have to learn those by heart, of course. It takes quite some time to calculate them. There's no easy formula for that. There's all kind of ways to get them. But if you ever need those at an exam, I will provide them as a little table. If you would need those expressions, but in general you can just, if you don't need the expressions, you can just work with them. Write P index as a function of x, and you know the properties. Oftentimes in exercises you don't even need to know what those polynomials are. You just need to know that they are eigenfunctions of the differential operator, as we shall see. Now, let's look at an application. Let's look at an application. One is to expand a function. If you have a orthogonal basis, and that is at least suggested now by Sturm-Liouville theory, orthogonality is guaranteed. If it is a basis, that has to do with is it complete and in what sense. I will come to that at the end of this presentation. But let's assume for the moment that it is a basis for a certain class of functions to be determined. But let us choose just a continuous function, this one over here. Then what we can do is use that basis, so we can use the Legendre polynomials to expand this function that is here. How do you do? Well, you just write that the function is supposed to be a sum, an infinite sum in principle, but we work with partial sums in the plot, as I will show brief shortly. So let's calculate that. Now let's first explain what I will do. So we write it as a sum of Legendre polynomials, and the coefficients of that expansion can be calculated by the projection formula using the inner product that I write with this bracket notation. So you take the inner product of, if you want to calculate the Cn coefficient, you take the inner product with the target functions with the nth Legendre polynomial, divide by the inner product of the nth Legendre polynomial by itself, and that provides you this Cn, so the weight coefficients in this sum for the nth Legendre polynomial. So that's the recipe, so then it's just a matter of pressing the button, calculate all those coefficients, and make the sum, and there it is in our graph. So this green function over here is this sum, and there's parameter n max here that I can change. And it means the sum starts at 0, so P0 with this weight coefficient, and then P1 with that weight coefficient, and P2 with that weight coefficient, etc., as much as we like and need. But it stops at n max, so I can show the value. It stops at 5, I have now 5 polynomials added up. And the function that I would like to approximate, as you like, in this way, is this one. And plotted as the blue dashed curved in this plot. And the Legendre polynomial, using 5 of the Legendre series, Fourier-Legendre series it is called, this series, including 5 terms, look like this. But let's see what happens if I increase the number of terms. If I have 10 terms or 11, I get a rather decent approximation. If I include 15 terms, you no longer see the difference. See, so it is indeed possible, and it does converge, as you see. If I add more terms, I get a more accurate approximation of that function, and if I add sufficiently many terms, it becomes really accurate. Now, it can be proven actually that the difference goes to 0 in this case, so you can approximate such a function as accurate as you like by just adding sufficiently many, and we can actually do this on the spot. So I can change the function. As you'll see, I change the function here, and the plot here changes, but now I have to recalculate the coefficients. And there it is. You can also, a different function can also be approximated. See? So it is really a matter of just applying the recipe I'd like to go back because there's another thing that I would like to demonstrate. That is the difference between the Legendre Fourier series and the Taylor series. It's a question that was recently put forward by a student who said, well, we already have the Taylor series, so what do we need the Legendre Fourier series for? Well, here's the Taylor series. Let's make the plot simpler by having only the Taylor series and the original function. So the original function is still the blue dotted one, and now we have a Taylor series of 4 terms. And let's see how that works. So if you start building a Taylor series with take only one term into account, so a partial sum, it picks the value of the target function at the origin. If you add one more term, so up to the first power of x, then you get the value right in the slope at the origin. And the more terms you add, the more derivatives are taken into account at the origin of at x is 0. So you get the value, the slope, the curvature, etc. will be mimicked by the Taylor series at the origin. And if you do that, you see that kind of the part of the domain at which the Taylor series is a decent approximation of the target function spreads out. So let's add many terms. Now you get further and further away from the origin, you still have a rather accurate approximation. But the key point is, it is really accurate and it becomes ever more accurate at the origin. That is the characteristics, the principle of a Taylor series. Now if we compare that to the Legendre series, that is fully accurate, as far as the eye can tell. But the convergence is different. So if we again start with, take only one term into account, only the x to the power 0 term, you see that the Taylor series gives the value of the function at x is 0. The Legendre series gives kind of an average value over the full interval. And the Taylor series, with one term taken into account, gives the slope at the origin, so you get a tangent line at the target function at the origin. The Legendre series gives a kind of a general slope average over the full interval. And that idea becomes more and more clear if you take some more terms. So this is a nice example. So the Taylor series, the purple dashed one, is kind of a parabola that follows the function at x is 0. The Legendre series is kind of an overall trend. So it tends to converge over the full interval as a whole. See? Now, and that is also the reason why if you have, let's say in this case about 10 terms added, take 10 terms into account in the partial sum, then the Legendre series is kind of accurate over the full interval, and the Taylor series has become very accurate at the origin, but away from the origin it is totally off. See? So both have their own characteristics, and both have their advantages and disadvantages. So it is really a matter of what you need and what you want in certain application context. But the difference is clear. The difference is clear, and you can also understand why it works as it works. The Taylor series is clear because you focus on the origin and add all the information about the derivatives there. And here we have an integral formula. So we integrate over the full interval, and apparently that makes the Fourier-Legendre series, as it is called, converge over the full interval in some sense, but we will come back in some detail to that at the end of this presentation. So that is the idea of expanding a function in the series of Legendre polynomials, and I already used the word trend, and that will come back in the next slide. So you can also look in the Legendre Fourier series can be used, and orthogonal polynomials more in general can be used to do trend analysis. You can look that keyword in the textbook of Ley on linear algebra. He also mentions that application of so-called orthogonal polynomials, and he has this kind of similar example as well in the textbook of his textbook on linear algebra, trend analysis. So that is an application of that, and then you think about data. So that is another example that I have here. So the same function actually, and I say, well, I generate data from that. So here it is. It starts at x is minus 1 and then in steps of 100. So I have about 200 points here. And they consist of the calculated values of those functions and a random number added. So you have this scatter plot. And the function is here. The blue line is this, the blue curve is that function plotted. But the blue dots is the values of that function plus some random number, so I get this scattered data. Now, I use that as a kind of a demonstration artificial data set that I make here on the spot. But it is something which you would have in practice if you do measurements. So I mentioned it lectures ago. There's a motivation for studying Frobenius theory. I already mentioned Legendre's equation, and I mentioned that can be used to model gravitational field. It does actually govern the dependence on the north-south angle of the gravitational potential of a planet, a rotating planet especially. And that is solutions of that equation, especially the Legendre polynomials, were used in 2000. Research that was published in January 2018 from the Juno mission to Jupiter, where the gravitational field of Jupiter was measured in great detail. Now data like that, the function would not look like that, but data would look like this. You have kind of scattered data, and the scattering comes because if you take a measurement, there's always disturbing influences that you don't know what they are about, but they have a little bit of influence on your data. So the real value that you would like to have measured is this blue line, say, like this blue line, but what you do measure is this scatter plot of data. And then the target goal is to interpret that. Now, that can also be done by using this Legendre polynomials, because I can construct a similar series, expansions in Legendre polynomials, and now I call the coefficient CD, D from data, but again, I have such a sequence, I can calculate them by the same projection formula, except that I recognize that the integral in the numerator, the top one, I cannot really integrate that because I don't have a continuous function here. I have scattered data at sample points. But the integral can be approximated by a Riemann sum. So I just sum over the data points at their subsequent positions, multiply by the dx, the delta x, which is this delta that I define here. The steps between x taken is this 0.1 in this example. So such an integral can be approximated by a sum. So I just replace, to see what happens, I just replace this integral in the numerator by a discrete sum. a Riemann sum, approximating the integral. And I normalize by Cn by just dividing by the inner product of Pn by itself, as I did on the previous slide. So this is a discrete approximation if you have data of that Cn, and this is the Fourier-Legendre series that you get out of that. Are very similar to the ones that we had in the previous slot. See? So if I add sufficiently many terms, about 10 say, I get a rather decent interpretation of this data. And now as Leigh says, and as I said in the previous slide, you can use that to do trend analysis. For example, if you take this series and take only the zeroth in the first term into account, you get a straight line. And it shows you that there's a tendency, a trend in the data to be skew, asymmetric. And that is this coefficient. That is the coefficient of the P1. This coefficient tells you, well, that is this slope. This coefficient. So in the Juno mission, they reported that they used so-called spherical harmonics. Now those are a little bit more just two-dimensional versions of what we do here. Legendre Polynomial, you take only the north-south component into account. If you generalize it and take also the east-west component into account, you get spherical harmonics. But the idea is the same. So they expanded their data, measured data, such a scattered data set, in terms of such functions that are orthogonal using such a technique. And then looking at the coefficients of your series, you can see the trends. And the trend that they were after actually was to see if the gravitational field of the Jupiter planet is asymmetric, so odd in the north-south, because if you look at photographs of the Jupiter planet, you see storms. That is a very turbulent, stormy atmosphere. The great red spot of Jupiter is a hurricane storm, huge, and that has been observed for 300 years or so. Galileo already saw that. So it's very stormy, and what they noticed is that if you count the statistics, there's more storms on one of the hemispheres than on the other. And a long-standing question for about 30 years was, are those storms deep or are they shallow? And if they would be deep, because a storm is, if it is a hurricane, you have a low pressure zone in the center, the core, so there's less mass. And if it is deep, and you have many storms on one of the hemispheres, and the storms are deep, penetrating into the atmosphere, that means that there's, on average, less mass on that hemisphere. And then you expect the gravitational field also to be skew, asymmetric. So gravitational field is on average a little bit less or larger at one hemisphere compared to the other. And that would be such a trend. So to find such trends from data, you can use this technique. So if you check the papers, and they appeared in the scientific journal Nature, January 2018, you see plots of the gravitational field of Jupiter interpreted in terms of spherical harmonics, looking for such asymmetries. And apparently this method was used to do the trend analysis that they were after in that experiment. Now that was a great scientific success, because knowing about the depth of the atmosphere of Jupiter is of importance to modeling the climate of Jupiter, if you like, so for climate science in general. So that is also very important, because climate is something that we need to understand better, and one way to do it is to think about climates at other planets, Jupiter inclusive. But you need to know such things. Is the atmosphere deep, and do a storm penetrate deeply, or are they very superficial? And this experiment was able to decide that by observation, and this was one of the techniques that they used. So that's a very nice and spectacular example of applying orthogonal functions, orthogonal polynomials in this case, in applications in science, really. So that's very nice. All right. Now back to our theory. I'd like to do a thought exercise. This is, if you ask me how does this arrive in a practical example, so I do not immediately have an answer. But that being said, it's a very good exercise to think about all the concepts that we developed and use everything that we know now about the concepts to navigate our way to a problem like this. So first step is, well, let's consider some function. A function that is nice to do exercises with. So I have this one. G, that is a parameter A and independent variable x, and that is A over the E, Euler's number, times x plus e to the power x, so the exponential function. So this E here is the same as the base number of the exponential functions. The question is, does this function have a component along the first Legendre polynomial? That would mean, if I would expand that function, would this coefficient here be 0, yes or no? That is what it means. Does it have a component in that direction? What is that coefficient, yes or no? Now the answer is, well, if the inner product of that function with p1 is 0, then it doesn't. So I calculate of this function the integral with the first Legendre polynomials, and there it is. You could do that. The first Legendre polynomial is just x, by the way. So you could easily calculate this integral, and I've done that. This is the result of that. It still has the parameter a, of course, there. So we conclude, well, if a would be minus 3, then this would be 0, then this integral would be 0, and then the answer would be no. And only then. So only if a is minus 3, then that function g does not have a component in the direction of p1, the first Legendre polynomial with index 1. So that is the function x, actually. Now, that is nice to know, but now the next question is this one that could emerge at an exam, by the way. So given that, now we consider this equation, which is Legendre's equation multiplied by a minus, and with the right hand side. So this is a non-homogeneous Legendre equation, as the title of the slide says. Non-homogeneous Legendre equation. And what could we say about it? Well, in an exam question I would be more specific, guiding what exactly I want to know. What in this thought exercise we look at this equation and we wonder, what can we say about that equation, given that this coefficient has the value 3, and we just have thought about and discovered that if that coefficient is minus 3, then that function does not have a component in the direction of p1. What can we say? Well, given everything that we learned about Sturm-Liouville, and now singular Sturm-Liouville, we say, well, if we would confine ourselves to the span of this set, the orthogonal Legendre polynomials, use that as a basis, it is an orthogonal basis because the problem is self-adjoint. If we require functions to remain in the span to remain finite. So we have a self-adjoint problem and we have an orthogonal basis here. And as we will see the general criterion is that the functions must be what as they call square integrable. So that is a technical remark, I will come back to that later. Yeah? But focus on the fact that we have an orthogonal basis of these orthogonal polynomials. We use that as a basis. And then we use that to see if we can draw some conclusions about that non-homogeneous Legendre equation number 1. And we say, well, to proceed, if we have a orthogonal basis, I can expand, at least formally, my functions y of x as a series in Legendre polynomials. And the coefficients of that I call y subscript n. So y subscript n is the nth coefficient in the expansion, the series, the Fourier-Legendre series of y of x in terms of Legendre polynomials. I find that a convenient notation. So the y tells you of which function it is, the coefficient, and you see the coefficient, and that tells you that it is just a number, a coefficient in the series expansion. So I find that convenient, and that is what it is. And likewise, I can expand, in principle, that function 3 with 3 minus, of g with minus 3 substituted for a, so this function, that right hand side there, can also expand as a function of Legendre polynomials, and I would call the coefficients g subscript n here. So I have two series. Now what is key to know is that the Legendre polynomials are eigenfunctions of this operator. And the eigenvalues are n times n plus 1. So, by the way, in an exam situation I would give that. I don't expect you to know all kind of special functions by heart and to know by heart exactly what the eigenvalues are. That is, I do expect you to know that as a good engineer, but that is not required to know it under the circumstances of a closed book exam. So that would be given. And it is, but that is information that we have. And that tells you that very easily. If you substitute this y into that operator, the operator is complicated, but the result is very simple. That is just n times n plus 1 times that coefficient times the Pn. This is the eigenvalue. See, if I substitute a linear combination into a linear operator, I get the same linear combination with the linear operator operating on the components. So it is linear, so the scaling factor yn just remains a scaling factor, and otherwise you get the eigenvalue, which is the result of the linear operator acting on the Pn times the Pn. And this minus 2 is this. If I substitute the y here, I get minus 2. Now, assuming that the series converges, I can distribute the minus 2 over the series, combine the series, and you get this. So this is simply the result of substituting y, expansion of y, in the left-hand side of that equation, using the fact that the Pn are eigenfunctions, and the eigenvalues are n times n plus 1. And the right-hand side is even easier. I just replace it by the series expansion of that function g. Now, and then again the set of Legendre polynomials is a basis. And we have expanded left and right-hand side with respect to a basis. So it is really like putting two vectors equal to one another. Both vectors are represented with respect to some basis. So you have the components of those vectors to the basis. But if the vectors are equal, the components are equal, must be equal, because it is a basis. Hence the expansion is unique. So there's only one way that you can expand each vector, or each function in this case. So if the functions are equal, the coefficients must be equal. with respect to that basis. So for each value of n, what you get here as a coefficient of that Pn must be equal to what you get over there as that function Pn. Now if you look at it, it allows you to calculate the yn. The gn should be considered as given because this function is given, and you can in principle just calculate the gn by the projection formula. But the yn are unknown because the y function is the unknown function of this problem. So the coefficients y1, yn at this stage are unknown. But now you can calculate them except if n is 1, because then this is 0. See, if I substitute n is 1, I get 1 times 1 plus 1 is 2, minus 2 is 0. So y1 is multiplied by 0, and hence the y1 is remains free. And all the others can be calculated. But that means in the left-hand side in the series, the coefficient of the p1 is 0, and that means in the right-hand side it must also be 0. For the problem to be consistent. And it was. And that is what we started with. We asked, does this function have a component in the direction of the p1? And we decided it does not. If a is minus 3. See? So it comes out right. So indeed, this problem is consistent. The y1 remains free. And it is consistent because the g1 is 0. The y1 is free. And all the other coefficients yn can be calculated just by equating. So you equate 1 by 1 and then the yn follows by dividing the corresponding gn by this factor. So that is this formula here, the result. The yn is gn, the corresponding gn divided by n times n plus 1 minus 2. That is this factor. And here again is the formula that you can calculate if you are interested in having the values of the gn. And I've done that on the next slide to show what it looks like. So the next slide has graphs of the right-hand side and the left-hand side of this equation when we substitute in the left-hand side this solution for the yn. And I can take more and more terms of the series into account. And then you get this. So this is two plots that I have. This is the right-hand side, and the dashed curve in green dashed is the right-hand side of the equation. So that would be a graph of this function. And having a solution for y would mean that if you substitute that solution of y in the left-hand side, what you get out of that, if you evaluate it, is equal to the right-hand side. But in the graph, I get the horizontal straight line, and that is because I don't take too many terms of the series into account yet, only one, namely. So, but if I take more, you see that the solution for y is represented more and more accurately, so the shape of the solution that we see in the left-hand side plot changes. And you do see that it does qualify as a solution, because what you get out of the left-hand side, the purple curve, if you substitute that y, ever more accurately approximated the right-hand side of the equation. See? So this is a rather decent approximation of the solution here. And that it is a decent approximation speaks from the right-hand plot, where we see that the result from substituting this function in the left-hand side of the equation gives a rather decent approximation of the right-hand side of the equation. And if the approximation is really good, then the solution is really a good solution, you might say. It's an accurate solution because it accurately satisfies the equation. So that is how that works. And so what I did to produce this plot is just calculate the results of the previous one, the previous slide. And one of the results that we had was that the y1 is free. Now I have that here as a parameter as well. If I change the y1, you see that the slope, that is the coefficient of the p1, so that is just the function x. So I add the function x more or less with maybe a negative or a positive coefficient. We can see so negative. You see the tilt of the function y. So I can change the function y, the solution y, in this way. You can change this about, but it does not have any influence on what happens in the right-hand plot. It does not have any influence, and that makes sense. That is correct because that function p1 is a eigenfunction with eigenvalue 0 of the left-hand side of the differential equation. So you might check that for yourself. If you substitute x in this equation, you get 0. So you can substitute x or any scalar multiple of x, you can add to y, because that doesn't change the outcome of the left-hand side. And that is indeed what we see here. I can add a multiple of x, change the solution, but that does not have any impact on to what extent it is a solution. See? And once again, by adding more terms to essentially this expansion of y, so increase the upper bound. The exact solution is infinitely many terms, but in the plot I have partial sums, so I have a finite number of terms that I plot. That is this upper bound, and the more I take, the more of these coefficients I add with these, the more of these terms that I add with these coefficients is calculated here by help using the results for expansion of z, the more accurate becomes the solution. See? So that is a technique to solve these non-homogeneous problems for the regular singular equations, in this case Legendre's equation. And because we understand all the ingredients so well, eigenfunctions, orthogonal bases, you can really navigate in the problem and understand what is happening, construct it. Well, now, to summarize the whole episode. So in this episode we extended the Sturm-Liouville formalism to allow boundary points to be regular singular points of the differential operator. And in this part 2 we saw as an example the Legendre differential operator from Legendre's equation, and indeed that has regular singular points at x is minus 1 and 1. And hence the whole Sturm-Liouville problem lives on that interval. And why is that? Well, we did revisit in part 1 the proof for self-adjointness, how to establish self-adjointness, and we concluded that in practical cases, and we saw an example now, it can be possible, it's even natural, to have self-adjointness as a consequence of, in this case, rather natural restrictions. I talked about the gravitational field of Jupiter, and you know, well, the functions are finite. There's no singularities there. So that's a natural restriction. If you impose it, well, I want to only work with the finite solution, so I only work with the Legendre polynomials and not all the other Legendre functions that are infinite. that have infinities, just work with those functions. That's a natural restriction. And if you impose those restrictions, you will have self-adjointness in this case. And hence, the basis that you have of Legendre polynomials is orthogonal. And eigenfunctions. And as we saw, that is really convenient. Now you see that for singular Sturm-Liouville problems, as we call them now, this all is very natural. You have these regular singular points, those emerge from the differential operator itself. And to impose conditions there, to have self-adjointness is natural, was needed, and natural. So it kind of takes the same shape as having a Sturm-Liouville boundary value problem, as we had in the previous chapters in the book, the regular Sturm-Liouville problems. But in some sense, in this context of having the regular singular points, is more natural. You don't have to impose the boundary points, they emerge from the differential operator itself. And the conditions emerge from the application, and combining those, you arrive in a rather natural way at singular Sturm-Liouville problems, and you discover the harvest is the orthogonal basis of eigenfunctions, and precisely the eigenfunctions that have nice properties as regard the applications. So it all comes together in a really nice way. Note that the boundary conditions that we impose in this context are rather mild as compared to boundary conditions that we had for regular Sturm-Liouville problems. Then we had the homogeneous Robin conditions, also general, but you do prescribe that they have to be homogeneous, there has to be zero there. Whereas here, we don't really say what the value must be, we only say, well, it must not be infinite. So that is a rather mild condition, and that adds to the flavor of these kind of problems to be this kind of natural, have a kind of a natural flavor, at least to me as an applied scientist. Now, as I mentioned, given suitable restrictions, for example, the functions that we want to work with, as we did in the thought exercise, we want to have finite functions that are in the span of the polynomials. The suitable restriction, and then given that restriction, the orthogonality itself really comes from the regular singular points, because those are the points where the coefficient function p is zero. That is the very definition of a regular singularity, and then you have to check it if it is regularly singular. What singularity in the first place comes from the fact that the prefactor of the highest order derivative, the y double prime, is zero. That is px, and the same px is zero at the regular singular point guarantees the self-adjointness. So again, things fall very nicely in place. Yeah, and then again, you do need a diagnosis of what exactly happens to all the solutions of the differential equations at the regular singular points, and that once again explains why we did chapter 5, including exactly that. So we have the Frobenius theory. That means we can really solve the problems in full generality at the regular singular points and really establish if the solutions are singular there. With the remark that in this case, the y1 solution of Legendre's equation, you can show that it is not singular at the regular singular point that you are studying. The question is it singular or not at the other regular singular point? So that is not a point where you would expand your solution about. Now, to show that, you'll need an additional, can be shown, using linearity and consideration of even, odd, of the functions that you get symmetry. You can prove that, but it is a little bit beyond the scope of this course, but it is based on the Frobenius theory again. So this remark applies that the Frobenius theory is really useful because it does allow us to come up with a full diagnosis of what happens at the regular singular points to the full set of solutions of the differential operator, and that you want to know. Now then, in general, last remark about singular Sturm-Liouville problems in general. This is also in the textbook. What is on this slide cannot necessarily be concluded from everything that we did study so far. So this is just additional information that I give without proof. One of the biggest differences between singular Sturm-Liouville problems and regular Sturm-Liouville problems is that the spectrum of eigenvalues can be non-discrete. So there can be continuous ranges of eigenvalues for each value you have an eigenfunction. Whereas in the regular Sturm-Liouville problems, as we saw in the previous sections, the eigenvalues are countable. And there's a lowest one, and they increase all the way to infinity, but it is a discrete countable set. That is no longer true for singular Sturm-Liouville problems, and you can have there can be a continuous range, or there can be parts of the spectrum that are continuous, one or more. So that is an important difference. But it was not the case for Legendre's equation, by the way. And it's still a countable discrete spectrum, as we saw, given the boundary conditions that we adopted, enforcing that we only have the Legendre polynomials. As is remarked in the textbook, by the way, if you have continuous ranges of eigenvalues, then you can no longer sum. If you try to expand the function in terms of eigenfunctions, you can no longer sum over an index, but that is then replaced by integrals. And we will meet an example of integral transforms that you then get. Laplace transforms that we will study in the upcoming episodes are examples of integral transformations. So we will see an example of how one function can be represented as an integral of other functions. Something similar would happen here, but we will not go along that road. We have to stop somewhere, and that is now. But that is what happens if you push the boundaries of Sturm-Liouville problems even further and go and explore those continuous ranges of eigenvalues. Then the question of completeness. I really used the notion of having a basis, expanding functions with respect to a basis, but that is a subtle matter. It's not something that we go into in any detail in this course. We just say, well, I just assume that I can expand the functions that I'm interested in that basis, and whatever is in that span, I will accept, or I will inspect. We are scientists, we are engineers, we are applied scientists. So we apply these methods because they are convenient and we understand them to a certain extent, and that these are good theories. But at the end of the day, as we did in this examples, case study of the Legendre equations, you just make the plots of what you get and you can inspect your results. Now, that is wise in this case because of this. What is exactly in the span of such a basis? Yeah, you better make plots to see what it is that you get. So quite in general, you have these expansions, and I've written, I write any function f as a sum of, infinite sum, weighted sum of eigenfunctions of a Sturm-Liouville problem, singular Sturm-Liouville problem in this case, weight coefficients fn to be calculated by the projection formula. And the question is, if I take the limit of the upper bound of that series, does that converge to that function f? And if so, in what sense? How precisely? That is a tricky matter, as we also saw it for the Fourier series, where you have this Gibbs phenomenon. So that is an example of that you sometimes have to conceive the notion of convergence in a rather subtle manner. So it's just wise to have the plots or take additional courses later in your career to learn more about that. But this is as far as we go with that. With the remark that such convergence is in practice formulated and understood in terms of minimizing this error. And again, I have here the inner product notation. I have the inner product, open bracket, close bracket, comma. And this is just the inner product of the difference of this function s, f, with these partial sums s. So I calculate a norm, which is equal to, in the Sturm-Liouville theory, to the square averaged integrated over the interval where the Sturm-Liouville problem lives, so where the orthogonal basis comes from, with the weight function as we saw Rx. So this is a kind of the area of the square of the difference of those functions. So that is a square, least square error. This is why we call it Rn. So each partial sum n, you can classify that by associating with it this square error. You could take the root and you have at least the square root error. We just can look at the square error. And it's not so difficult to show. That is done in the textbook, by the way, that if you construct a series like this and calculate the coefficients like that, then this error is minimized. That can be easily shown. The difficulty is to show if the limit is 0. So this series minimizes this error, the square error. The subtlety is to show if that limit goes to 0. Now that has to be done on a case-by-case basis, typically, or by subclasses of problems. One subclass that I can mention that applies to the Legendre polynomials is for orthogonal polynomials, the theory can be done standalone. So we discovered orthogonal polynomials as solutions of Legendre's equation and recognized that this is a singular Sturm-Liouville problem, self-adjoint, and hence the polynomials must be orthogonal. So for us, they arrived from that context in a natural way. If you look in the textbook of Ley, you find the same orthogonal Legendre polynomials, but as a standalone subject. Then the inner product is just defined, and by the Gram-Schmidt procedure that you can always use to produce an orthogonal basis, you can also produce an orthogonal basis of polynomials defined on the interval between -1 and 1. And then you find exactly the same Legendre polynomials. In mathematics, the theory of all such orthogonal bases of polynomials on finite intervals is a standalone subject, linear algebra and analysis, and for those bases it has been proven that they are complete. So they converge in this sense of a square norm, and the limit for n to infinity of that error is 0. And that's, so you have convergence, the limit goes to 0, and the measure that you have to measure the difference between the target function and your partial sums is this. So, now, sometimes students ask me for further reading. They find the subject interesting. Sometimes I get requests, Professor, do you have additional books that we can use to learn more about this? Now, a nice book to learn more about this, orthogonal functions, orthogonal polynomials, and that has the proof of convergence and completeness, is a book by Hoogstad, 1971, The Functions of Mathematical Physics. Is of course not required for this course, but if you would be interested to learn more about this, and just to mention that this course is just an introductory course, and you can spend your career studying, then there's books about these things. All right, well, that concludes, I think, our studies of Sturm-Liouville problems, with, I think, a very nice result that we showed that there's a thread in the course that goes from the Frobenius theory, the regular singular points, in chapter 5. In fact, in chapter 10, if you do separation of variables to solve a partial differential equation, you find these kind of equations that have regular singular points. And now at the end of chapter 11, we see again that in a very natural way, those regular singular points also are the source of finding orthogonal bases. And as we saw in chapter 10, that is very profitable. Again, in the example that we discussed today, we saw once you understand it, that you have an orthogonal basis, you know how to use it, the problems simplified in a very substantial way, so it's very good to have. And you see also the thread throughout the course, how all these different pieces of theory combine at the end of the day, form one framework to work with. So I think that is very satisfying, and I think that is a very nice end of this episode.